3, we'll be doing exactly what we did in 10.2 with the hypothesis test, except for this time, we're trying to say yay or nay on claims made about the mean, okay? And that's the only difference. So the only difference will be when we go to do our test statistic, it won't be a z-test statistic, it will be a t-test statistic, and this is a formula we'll use. And then we'll have to use our golden chart for our t-values to find our p-values. T-values and p-values and all kinds of values going on, okay? Of course, we have to make sure our sample is random, and that's something to kind of mention in our M&M project that we just did. It wasn't really a random sampling. Like, I went and got a box of M&Ms from Sam's. What would have been really random is if I told all of you guys to go buy a pack of M&Ms, because what would be the odds that you, all 20, got them from the same store, right? So that's a little bit more random sampling. They're just way cheaper to buy in bulk, so that's why I do that. And you guys have to pay so much for the class anyway. I don't want you to have to spend $1 or so on M&Ms. Make sure there's no outliers, and also if it doesn't say it's normally distributed, your sample size has to be greater than 30. And that's just something that we talked about in Chapter 8. So go ahead and flip it over to the top of page 8 here. What you're going to notice, guys, is I don't even give you steps or anything because they're the exact same steps. Nothing is new. We're still doing 1 through 6. The only difference is when we go to do our test statistic, we're going to use that t-value formula. So it says, Karl Reinhold August Wunderlich said that the mean temperature of humans is 98.6 degrees Fahrenheit. So those in the health field, that's supposedly normal, right? Other researchers have thought that the mean temperature of humans is actually less than that. So what they did is they went and measured temperatures of 28 healthy adults. The sample data resulted in a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.7 degrees Fahrenheit. Test whether the mean temperature is really less than 98.6 degrees Fahrenheit with alpha equaling 0.01 and the distribution is normal. So again, they had to say this because what was our sample size? 28. So since our sample size wasn't bigger than 30, we have to have that normal distribution. All right, so let's kind of label stuff. What is the supposed mean temperature? 98.6. So what are we going to label that with? Mu. That's what the population supposedly is. Can you see that's way up there? All right. We went and asked 28 adults. So what can we label the 28 as? N. That's our sample size. And when we took that sample, what was our mean? 98.2. So what's that going to be? X bar, exactly right. So kind of remember that because they're going to throw 2 means at you. The first mean is usually always that mu, and then when you go and take your sample, that's the X bar. And then do you guys remember what the symbol is for sample standard deviation? You got it. All right, so we have everything. So we're going to state our hypotheses, the null and the alternative. And since we're dealing with mean, what's our parameter we're going to use? Mu. The null always has a statement of equality. And then what we're trying to prove is that test whether the mean temperature is really less than that. So then we have a less than or a left-tailed test, right? All right, less than what? The supposed population mean that they said in the very beginning, right? 98.6. And remember, when it's means, we can put units there. And you want to know why I remember this? So this is my 10th year teaching here at Lewis and Clark, and when I came to interview, they liked me, and so they had me teach like a class, and this is what we were teaching. And the only critique they had for me is I forgot my units. So don't pull a Molly and forget your units, okay? So whenever it's mean, we're going to put our units down. The level of significance, alpha, is what? 0.01. And what that means, guys, that means we have a 1% chance of making a type 1 error. And if you go back to that Punnett square, a type 1 error is saying reject when you shouldn't. So you're really hesitant to say reject. All right, the test statistic. I'm just pulling this from the bottom of page 7. It's T equals X bar minus mu all over S over root N. So it's just like 8.1 or 8.2. It's 8.1, I think, but instead of sigma, we use S. All right? So we've labeled everything, so we should be able to fill in our numbers. What was our X bar? 98.2 minus our mean, 98.6 over S, 0.7, and then the N of 28 is the only thing in the root, guys. All right? In order of operations, do each of them kind of individually. So do that subtraction by itself first and get negative 0.04, right? And then do the 0.7 divided by the square root of 28 on its own and round to 4 or 5 decimals. For some reason on today I rounded to 5 on this one. So I got, oops, not 0.4, it's just 4, isn't it? Sorry. Make sure that's 0.13229. Does that look right? So when you do that division, negative 0.4 divided by that standard deviation, you get a t-score. And this is something that's new that I probably wouldn't count you off on, but t-scores are actually rounded to 3 decimals, which is weird. I know you're not used to that, but that's what t-scores are usually rounded to. All right, so our question is, and to me, I would quickly, like if I wasn't doing this statistically, I would look at that and say 0.4 of a degree is not that big enough difference to say that it's different, okay? That's how I would read it initially, but it actually is quite a big difference, and so we'll see what happens. So this is where, like, I feel like using your chart and doing it by hand gets kind of awkward. So I feel like using your calculator on your T1s are a little bit better because you can get the exact p-value, where here we have to estimate, okay? So to determine our p-value, this is what's weird, is these are technically our p-values up here. It's the probabilities, they're up there. And our t-test statistics are in here. So it's a little bit backwards. What we have to do is we have to go to the correct row. Do you remember how to find the correct row? It's our degrees of freedom. So we're going to have to subtract 1 from our sample size, so we're going to have to go to row 27. Then once you go to row 27, you skirt across it, until you find 2 t-scores that your t-score falls between. And don't worry about the negative, because we know the area in the left tail is the same as the area in the right. So we're looking for t-test statistics that straddle 3.024, okay? So you go to row 27, and you got to go pretty far over. Here we're at 2.771, and here we're at 3.057. So do you agree that our 3.024 is in between these two? Okay? Which means our p-value, we don't know exactly, but our p-value is between 0.0025 and 0.005. So let me write that all down, because you're following along today, but then when you go look at your notes, you're like, where did that come from? So determine the p-value. So our row, guys, is degrees of freedom n minus 1, which is 28 minus 1. So we went to row 27, right? And then we scrolled to find what straddled .024. Okay, so we found, what was it, 2.771 and 3.057. Is that our answer? No, that's just kind of getting us to the right point to where to look, right? So where is our p-value? Our p-value's in the middle. And what I don't like about this chart, guys, is our chart goes from high to low, which is the opposite of what intervals should go. You know, with inequalities, you should go low to high. So we're really looking at the 3.057 one first. So our p-value is between 0.0025 and 0.005. That's our p-value. Okay? So we went to the correct row. So we went to row 27, and we scrolled to find what straddled our value of 3.024. The 2 t-test statistics that straddled it were 2.711 and 3.057. The 2 areas that went with them, make sure you have low then high, and that means you always have to flip them. The 2 areas that went with them was 0.0025 and 0.005. Even though we don't know our exact p-value, we still can compare it to alpha, right? So look at our p-value, guys. It's less than 5, what is that? It's less than 0.5%. Right? And so is that weird? Yeah, that's easily less than 0.01. So are we going to reject or not reject the null? Reject. We're going to reject the null. So reject H naught, since the p-value is less than alpha, right? Do we know the p-value? No, but always kind of use your upper bound, because your p-value is less than the upper bound. And if the upper bound is less than your alpha, was that guilty with association kind of thing, right? Like, we know that we're less than 0.005, so 0.005 is definitely less than our 0.01. So always kind of use that upper bound to gauge. Does that make sense? We don't know the exact p-value, but if we're less than 0.005, and that's less than 0.01, then we know we're less than 0.01. Since we're rejecting the null, what's our conclusion going to be?
There is sufficient evidence.
There is. We have enough, right? So there is sufficient evidence to support H1. And again, I'm fine with H1, but my math lab will be wordy. They'll have, there is sufficient evidence to support the claim that the mean temperature in humans is really less than 98.6 degrees Fahrenheit. So again, try to soak it in. Somebody thought it was less than 98.6 degrees, so they went and took the temperature of 28 adults. The average was 98.2. So based on the assumption that the average was really 98.6, we had less than 0.5% chance of getting our average of 98.2, but that's what we got as our average. So something's weird. I bet we're far off of 98.6, so that's why we're going to reject it and be able to support this, okay? Can I show you how we do it in our calculator just to show you that you can actually get the specific p-value? So grab your calculator. I'll just talk you through it. You know where to go. So it's the back of the calculator sheet that I got you on Monday. You're going to go to the same prompt. You're going to go to test, and instead of one prop Z test, you're going to a T test. You're going to go to a T test, okay? And you're going to choose statistics, right? What's the first thing it asks you on your T test? Your mu, right? So what was the supposed average temperature? 98.6. And then does it ask you your X bar, your sample?
Yeah.
So then you're going to put 98.2. Then does it ask you for your S? 0.7. And then does it ask you for your N? Let's see if I can think this. Okay, so let me go. And when you do this, guys, they will actually be able to calculate the exact p-value, where we are just using a chart, so we don't know any better, okay? So I'm going to go to Stat, scroll over to Test, and I'm going to choose T-Test. So remember you chose T-interval for 9.2 when you're dealing with means. You're going to choose a T-Test for 10.3 when you're dealing with means. Data is if I gave you a bunch of, like if I gave you all their temperatures, and you put that in list 1, you can say, hey, look at list 1 and tell me the mean and stuff like that. Stats means they already gave you the stats. They already gave you the mean and the standard deviation. So mu was 98.6. I know, like, you guys already have this done. Our standard, or our average was 98.2. The standard deviation was 0.7 of a degree, and then our N was 28, right? So we wanted to prove that it was less than. And again, match the sign, not the mu. Match the sign, not the mu. And hit calculate. So notice their test statistic is spot on with ours, right? Negative 3.024. And then notice the p-value. So maybe we'll write this off on the side. According to our calculator, our p-value equaled, oh, you can't see it right now. I got to go back and forth, sorry. According to our calculator, our p-value is 0.0027. According to our calculator, our p-value is 0.0027. So your calculator is able to calculate it exactly, but notice 0.0027 falls between our two bounds, right? So we were right. It's actually closer to the lower bound, 0.0025. 0.0027 is barely more than that, okay? But you can get it specifically. So in MyMathLab, bless you, on MyMathLab, sometimes they have you pick the range. Like, you don't have to type it, you just pick the correct range, like this, okay? Or sometimes they ask for the exact value. If they ask for the exact value, you have to do it using your calculator, okay? If you use your calculator throughout the whole thing, that's fine. Just be okay to say, this p-value is between this range, so that's why that range is the right one, okay? So the calculator will never fail you. You can do every single 10.3 problem with your calculator if you need to. All right, let's do this last one, and I mean last one. Woohoo! A company claims the mean pH level of a river is 6.8. You select 19 random samples of water and find that the mean pH level is actually 6.7 with a standard deviation of 0.24. At alpha equaling 0.05, is there enough evidence to prove that the company is wrong, assuming the distribution is normal? So, all right, anybody like in, I don't know, is it biology, where like neutral 7, I believe, for pH, and if you're are you basic if you go lower or acidic if you go lower? Acidic if you go lower, and then basics if you go higher? I don't know, one or the other, right? So this is kind of creeping a little bit away from 7, okay? But they're trying to claim, 6.8, that's not bad, it's close to 7, that's what it is, don't come test our waters. Well, we do. And we find that it's 6.7. So the question is this 1/10 of a difference in our pH level enough to say, eek, check your water, you're not very close to neutral anymore, all right? So we're going to state our hypotheses, the null and the alternative. We're talking about mean, so let's go ahead and label our stuff. So the company claims that the mean pH level is 6.8. So what can we label 6.8 with? Mu, right? That first sentence usually has your mu. You go select 19 samples of water, so what can we label 19 with? N. And you find the average to be 6.7, so what can we label that with? X bar. And the standard deviation is 0.24, what can we label that with? S, okay? And at that point, the second you can label all those things, you can do the rest of the problem, right? So what do they claim it is? They claim that it's 6.8 pH. I don't know what, does pH have a, I don't know. There's a unit there, so we'll just make sure. That's not the right unit, but we're showing that we know it's units, right? And we're trying to prove the company wrong. How do we prove that it's wrong? Doesn't equal, right? So even though our average of 6.7 was less, we don't care. We're just trying to prove they're wrong, so we don't care in which direction we prove that they're wrong. So we're going to use mu is not equal to 6.8 pH. So what kind of test is that? And so we're going to keep that in mind if we're doing it by hand, all right? If we're doing it on a calculator, our calculator does it for us. Alpha is 0.05. What is alpha? It's the probability of making a type 1 error. So it's 5% chance of saying reject when I shouldn't. All right, so let's flip it over. So computer test statistic, it's T equals X bar minus mu all over S over root N. Our X bar is what we found when we took our sample. That was 6.7 minus the supposed average of 6.8 over, I don't remember what S was, 0.24, okay? And then S was 0.24, and we had 19 in our sample. So both of these that we did today, guys, we had less than 30, so they had to be normal. It had to be stated that they were normal. All right, when you do this, I got to catch up with you because I got to turn my page here. We have negative 0.1 over 0.05506 is what I got. Does that look right? So I always do the difference first, get the negative 0.01, and then do that on its own, round to 4 or 5 decimals. So I got a t-test statistic at negative 1.816. Does that look like what you got? And if you're, some of you kind of, I saw you kind of type it in your calculator, make sure it looks okay in your calculator as well. All right, what is the p-value? Again, let's just do it by hand once because I just want you to get kind of familiar. What row are we going to go to? Degrees of freedom are n minus 1, so we're going to go to row 18, okay? So get this little guy out and screw it across row 18 until you find 2 t-scores that straddle, and again, I don't care about the negative, the 1.816, okay? So go to row 18, and we're going to see what straddles 1.816. These two, does that look right? 1734 and 2101. So what are the two p-values? 0.025 to 0.05. I'm going to write all that down, okay? So we went across and we straddled 1.816, and we found that it was between 1.734 and 2.101. Okay, again, that's not our answer, that's just where our p-value is going to lie. So our p-value, remember to flip-flop which one's where. So the further one, 2101, is further out, so it has a smaller area. So 0.025 is on that end. And then the larger one is 1.734. It's not as far out. That has an area of 0.05. And I'm running out of room. But am I done? No, because what kind of test was this? Two-tailed. Do you remember what we had to do with two-tailed test? Double it, okay? So you're like, oh my gosh, I don't even know what my p-value is. How do I even begin to double it? You just double both the ends, okay? So all we're going to do is times it by 2, and you'll get 0.05 to 0.10. Is that okay? I'm putting a little asterisk there. We're doubling it because it's a two-tailed test. So, and notice on this one, it would make the difference between rejecting or not rejecting. Is everybody okay that when I doubled it, I just doubled both bounds, okay? So when you double 0.025, you get 0.05. And when you double 0.05, you get 0.10, okay? So, let's do it. Can we do it on a calculator real quick to see what we get so we can find our exact p-value? So, how am I doing on recording? I hope okay. So, we're going to go to tests, or excuse me, stat, scroll over to test. We're going to go to number 2, a t-test. We have statistics, and our average was 6.8, but our sample average was 6.7. And our sample standard deviation is 0.24, and our sample size was 19. And we just want to prove them wrong, so that's just the not equals. And then we hit calculate. So again, notice our t-test statistic matches the negative 1.816. But then what can you get for your p-value? 0.086. Is that what you guys got? Notice it falls in those bounds that we had set. We said it's somewhere between 5 and 10%, and it's like 8.5%. So kind of going back to our notes, if you want to make a little note, our calculator says that the p-value is 0.086. So on the test, guys, I'm going to be accepting either one. If you're like old school and you're like, I like to do it by hand, I like to use a chart, I will be looking for this. But if you use your calculator, I'll be looking for this. Both of them are correct because both of them you can compare to your alpha, right? So we have to determine whether to reject the null or not. So if the average was really 6.8, we had about a 9% chance of getting our sample average of 6.7. 9% is not the highest, but it's still not that weird because who do we compare to? Alpha, who was 0.05, right? So are we going to reject or not reject? Do not reject, okay? So do not reject H naught since the p-value is greater than alpha. And again, you can either use 0.086 or you can use 0.1. Either one is greater than 0.05. But if you were doing it by hand, guys, and you forgot to double it, you would have been rejecting, right, when you shouldn't have. So be careful on a two-tailed test, but that's the only time you double it. So if we're not rejecting, what's that mean for our conclusion? There is not sufficient evidence to support H1. What does that mean? As much as we were trying to prove this company wrong, like, oh, I don't think your water is close to 6.8, does it mean it's 6.8? No, we just don't have enough evidence to prove that it's not. So we're not going to reject the null, and we're going to leave them alone for now. We might come back in a year or so, but we're going to leave them alone for now. All right, so the last concept, I think, is really kind of what you guys probably think in your head. Because you're doing this, you don't really care. You're not going to do it in the real world. But I want to show you what the difference between statistically significant versus practically significant, okay? So it says, large sample sizes can lead to results that are statistically significant, meaning the sample is off enough that we can reject it, while the difference between the statistic and parameter are not that big of a deal in real life, all right? So I'm going to have you guys write down something real quick. Hold on a second, let me get this stuff for her. This is the only thing that's due on Monday. That stuff won't be due until Wednesday. Okay, so looking at this, guys, I'm going to have you write this. I'm going to grab my printed sheet, and then I'm going to sign online to prove to you what this is meaning, okay? So can you guys read that okay, the red? Will you write that down? just because it works out statistically that we can reject the null and say that the difference is big enough, the true difference in the two values does not always mean a whole lot in the real world, okay? So even though mathematically we can do this test and reject, the true difference in the real world is not that big of a deal. And I have a perfect example of where this happens. I'm going to get it in the book and show you. And if it cuts off, it cuts off. I'm not going to worry. So just because it works out statistically that we have to reject the null, like the difference is big enough, the difference in the real world is not usually a big deal. If my math lab lets me do it.
I have my book.
Oh, God, of course you do. Thank you. Man, you've been pretty good about bringing that every day, huh? Yeah, because it's just loading and loading and loading. I need page 455, if you can grab that. Okay, so what it is, and this is what's crazy, guys, is in the real world, when they change stuff up, they actually do hypothesis testing to see if their change made a difference or not. So, has anybody heard of IDOT? Illinois Department of Transportation, like engineers are in there. My husband actually just got a job with them this summer. So he's in the engineering department. He's more with the roads and all that kind of stuff, but, yes. So what's going on here is, this is actually TDOT, the Department of Transportation. So what they did was they felt bad for the commute times. They thought the average commute times was a little high, and I'll throw it under here in a second. And so they thought they would reprogram all the traffic lights. Do you ever drive through town and you just feel like you're hitting one and then not hitting another? It's just like not consistent, just I get to drive through. Because supposedly you're supposed to be able to drive. If you get a green light here, you should be able to get a green light everywhere if you're going the speed limit. But that's usually probably our problems. We're probably not going the speed limit, right? So it says, according to the American Community Survey, the mean travel time to work in Collin County, Texas in 2013 was 27.5 minutes. The Department of Transportation reprogrammed all the traffic lights in Collin County in an attempt to reduce the travel time. So to determine if there was evidence that the travel time decreased as a result, the Department of Transportation obtained a random sample of 2,500 commuters and recorded their travel time to work and found a sample average of 27.2 minutes with a standard deviation of 8.5 minutes. So basically, guys, is 27.2 minutes that big of a difference between the 27.5? It's 0.3 minutes. That's like a third of a minute. What is that, 20 seconds? Does that seem like a big deal to you? Not really, right? But you'll see that when they do the math, it's statistically significant. So they want to prove that it reduced, okay? So they have a left-tail test. They do the formula using their sample mean and the supposed mean and all that jazz. They get a test statistic of negative 1.765, and they get a p-value that's between 0.025 and 0.05. So they actually get a p-value of about 4%. What does that mean? It means if the average was still 27.5, they've had about a 4% chance of getting an average of 27.2. So it's less than alpha. They're able to reject the null. So they are having enough evidence to support the claim that the mean travel time was reduced. Okay, so this is the example of that it was statistically significant. The TDOT people can say, yes, we did our job. We reduced the commute time. When the normal everyday person would you even notice a 20-second difference in your commute? No, that's the difference between picking up your phone one last time before you get out of the car or waiting for that person to cross the crosswalk. You know, 20 seconds in real life is not a big deal, but when you get that really large N, 2,500, you're able to prove a lot. And so they were able to prove statistically that they could reduce the mean.